All right. Well, this morning we're going to talk about root locus. And so it's pretty exciting because this is our first, we've done some simple design, but this is really our first design tool, right? It's by far not the only design tool that we'll have in our arsenal, but it's our first design tool. And root locus is simply what it says. It's basically a plot of the poles of poles of the closed loop transfer function. So closed loop transfer function as the feedback gain, which is usually K, but as the feedback gain varies. Okay, so a plot of the poles, right? That's basically root. And then, so the poles are the roots, and then basically how do those poles move? And that's where this locus comes in. And before we get into the details, I think it's easiest to look through a couple of examples. One is our CD player from way back when, right? We had R of S was our desired angular velocity. We had a feedback gain here, K. We had a transfer function that looked like this, right? 4 over 2s plus 1, which was G of S. We had C of S, which is our actual angular velocity. And then that velocity was fed back, right? So, so again, this is our angular velocity. And this is desired angular velocity. Okay, so one of the things, so what we're going to do, eventually we're going to do is we're going to find the closed loop poles from the open loop transfer function. But for right now, let's just go ahead and find the closed loop transfer function. So we've got C of S divided by R of S is equal to K G of S over 1 plus K G of S. We plug values in and do just a little bit of simplification. Well, we end up with 2K over S plus 4K plus 1 divided by 2, right? And this is equal to T of S, our closed loop transfer function. All right, so let's, so this is T of S, and just to remind you, right, K G of S was 4 over 2s plus 1. Or if we want to divide this by 2, right, 2 over s plus 1/2, right? And so with that in mind, right, so here is our open loop transfer function, and here's our closed loop transfer function. So closed loop transfer function, open loop transfer function. Okay, so when we're doing our plots, we're going to look at open loop poles and closed loop poles. right? So our open loop poles, right, from kg of s, well, we only have one open loop pole, is at s equals minus 1/2. And we don't have any zeros, which are going to be important as well, but we don't have any in this case. And then our closed loop transfer function poles, closed loop transfer function poles, which come from T of S are, right? So our S is equal to minus 4K plus 1 divided by 2. Okay, so let's do, so with our locus, we start with our open loop system. All right, so, and this is just our complex plane here, right? So I've got imaginary, I've got real, I've got 0, 1, 2, 3, minus 1, 1, 2, minus 2, minus 3, okay? And so our open loop transfer function poles, we're going to use x's, right? So we're going to have an x here at minus 1/2. So open loop transfer function poles, we're going to use x's. And then for closed loop transfer function poles, we're going to use triangles. Okay, so let's just see how that our closed loop transfer function poles change versus k. So k, and so our closed loop transfer function pole. So we have k is equal to 0. So at 0, just plugging into this equation right here, right? So we have 0 basically at minus 1/2. And in fact, right, if you look at it, when k is equal to 0, our open loop transfer function pole is the same as our closed loop transfer. Our closed loop transfer function pole is the same as our open loop transfer function poles. And that's, we're going to see that all the time. And basically, I mean, when k equals 0, right, we're basically setting this equal to 0, so we don't have any feedback, right? That's just when k equals 0. All right, so what happens then is we increase k. So at k is equal to 1/4. If we plug this in, we get minus 1. All right, so this is k equals 0, k equals 1/4. We keep going, we've got 1/2. We end up with minus 1.5. And then by the time k gets to 3/4, we're at minus 2. So this is k equals 3/4. And k is equal to k is equal to 1/2. So it's pretty clear what's happening to our root locus, right? We're starting at our open loop pole, and we're going out here towards infinity, right? So this arrow, this is basically the root locus for this simple system. It's just this straight line. It starts at it starts at minus 1/2 and goes out to infinity. So this is our root locus. And the arrow, which are important, arrow is in the direction of increasing k. Okay, simple as that. Now, I said we could use this for design. right? So let's say that we want group exercise here. Let's say we want a settling time of 4 seconds. All right, so what I want you guys to do is go back and use our rules, right, for calculating the settling time and where the closed loop transfer function poles are. And tell me what value of k is. What value of k you need to get a settling time of 4 seconds. All right, so I'm going to pause right now, and we'll get back. We will, when we come back, then we'll